Hi, I'm Igor. I'm a core developer at Calimero, and today I'm going to talk about privacy-preserving bridging using zero-knowledge proofs on NEAR and Calimero. So first of all, in case you don't know what Calimero is, let me tell a sentence or few. So Calimero is a NEAR sidechain. Its primary users are either governments or enterprises that want to use blockchain, but they don't want to put their sensitive data on a public chain, so we have this permissioned chain. And the thing that naturally you can ask, why would you put data on a permission chain? Like, what can you do with that? So that's why we have built a bridge. So you can, besides bridging just the FTs, the assets, you can also make cross-chain contract calls from mainnet into Calimero and back and get callbacks. And it's pretty fast, so there's a lot of use cases that arise from that. This presentation will be about two things. The first part will be the Calimero bridge that's currently open sourced and audited, and it's released. Anybody can use it. And the second part will be about the privacy enhanced bridge. This is something that we've been working on lately, and for this part, it's required that the audience knows a bit about zero-knowledge proofs in order to follow what's going on. So the Calimero bridge, as I said, allows you to bridge FTs, NFTs from NEAR and Calimero and back, and you can also do cross-chain contract calls. So the bridge itself, it's trustless. What does it mean? It means you don't need any kind of a central party or even a multi-sig that's approving something, but all of the proof-of-stake rules of NEAR are implemented in a contract. Most notably, any block that's being added to the contract, which can be added by anyone if you call the light client contract, 2/3 of the signatures on the block need to be signed by the validators of that epoch. And we are able to do this really fastly because of specifics of NEAR. It's automated, meaning that we have the bridge service through which it automates all the calls that are being made, and I'll show you what does this mean. There's a bunch of things going on, and we call it's kind of magic that it works this fast. It's very easy to use. You only need to sign one single transaction, and assets will end up on the other side, on the other chain. And it's pretty fast. It's 5 to 10 seconds to bridge assets or to make cross-chain calls, depending on the use case, how complex the contract is. So some basic terms, so it's easier to follow. Relayer is the simplest component. It simply reads a latest block from one chain, relays it to the other chain, sends it to the light client contract. The light client contract, as I said, in it we have implemented the validation of proof-of-stake rules inside the contract, so it's fully trustless. You push a block to the contract. If it passes, the block Merkle root hash for that height gets written into the state of the light client contract. And we have the prover contract, for which if you provide some proof in the form of Merkle paths, you can prove whether something happened on the other chain. On this chain, you can prove whether it happened on the other chain. And of course, we have the connector contracts for the FT, NFT, and cross-chain contract calls. Through these connectors, which use the prover contract, you either mint or burn and unlock tokens. FT and NFT are pretty similar. I will not go into these details. Let's see how to do a lock on NEAR side and mint on Calimero side. So on the left side, we have the Calimero blockchain. On the right side, we have the NEAR blockchain. So each of them have already deployed a light client contract, a prover contract, and the connector contracts. Down here, the components are also the validators through which they calculate the ordering of transactions. They essentially come up with the consensus, the archival node and indexer, which also enable to read into the historical state of the blockchain. The same things we have on the NEAR blockchain as well. In the middle, these are off-chain components, the relayers, bridge service, message queue. There's also events indexer and NEAR lake, which populate the message queue, but let's see how this works. Okay, so a user comes, and the user wants to bridge some FTs from NEAR to Calimero. How does this work? They will call FT transfer call. On the FT token they want to bridge. Here it's USDN, it's some stable coin, let's say. And they will, when they call FT transfer call, they actually transfer the tokens to the FT connector. So the assets will be locked here. Immediately when the assets are locked here, an event is being emitted from the contract, and these events will be picked up by the events indexer, which populates the message queue. And on the message queue for specific Calimero events, we have the relayers and bridge service subscribed to this topic. So the relayer immediately realizes somebody wants to do something with Calimero. The relayer then goes to the archival node and fetches the latest light client block from NEAR side. And it tries to add this light client block on the light client contract on Calimero side. If all of the proof of stake rules are valid, the block Merkle root hash for that height of the latest block will be added in this light client contract. And the property of the block Merkle root hash root is that you can efficiently prove that any transaction in history up to that block happened on blockchain, like provided with some Merkle paths. The bridge service also receives this same event that somebody locked assets. I mean somebody, this user, which is also written in the event. So the bridge service will go to the light client contract, fetch the latest known height. If this height is higher, at least high or higher than the block where this locking happened, the bridge service can fetch the light client proof data in form of Merkle paths. It will try to prove and mint on the FT connector on Calimero side whether this proof is correct. So it will go to the prover, calculate the block Merkle root hash. If it's the same as the one stored in the light client contract, it's safe to mint the same amount of tokens on Calimero side. So with this, we have proven on Calimero that somebody locked FTs on NEAR side. And all of this happens in 5 to 10 seconds. So burn and unlock, I will not go into details of this. You can look the presentation from NEARCon from last September if you want. This is just symmetrical if you go the other way. Here you burn and then you can unlock if you prove the burn happened. For the cross-chain calls, the proofs are also pretty similar. The only difference is that in the event you have you denote which contract address you're calling on the other side, what contract method, what are the contract arguments, and what will be the callback method when either the contract execution fails, or if it doesn't fail, you get back the execution with the result. Okay, so there's obviously some room for improvement in this approach, because currently any observer on the NEAR mainnet can conclude how much assets are locked in some Calimero chain by simply going and pinging what's the balance of the FT connector, since all the FTs are locked on a connector on NEAR mainnet. So it's kind of a similar problem as the Constitution DAO, if you're familiar with that. So what's the Constitution DAO problem? So there was an auction to buy one of the last physical copies of the US Constitution. And there was an auction, and this DAO wanted to buy it. And some private investor came in at the last moment and saw, oh, the Constitution DAO, they're on Ethereum. You can see what's the treasury, like how much money they have. At the moment, they had $42 million at that price of Ethereum at that time. And some private investor came in and just bid with 43 million, and they easily outbid them. So this is a problem when the treasury is, when you can know for some group how much money they have. So what we have built a solution so you cannot conclude when you lock FTs, where will they end up? So how did we build it? We built it using zero-knowledge proofs. Let's see how. So this is the problem we want to do. Some user wants to lock some FTs. They will lock it in a new connector, which is called zero-knowledge connector. And what will the outsider know and what they won't know? So they won't know where the tokens will end up. Where will they be minted? To whom are they meant for? What they will know the total sum of all assets. So if 4 of these chains are using it, they'll be able to tell the sum, but not how much each specific chain has. So in order to show you how we do it, I need to introduce a bit of finite field arithmetic. So we define some group G that has a generator, small g, and we take it to the power of 2, to the power of 3, to the power of some large prime number q minus 1, and all of this is modulo this large prime number. And specifically, we take the points from the Grumpkin elliptic curve out of this group. Why do we use this elliptic curve? Because it's efficient to create ZK snarks with this curve. Also, we use Schnorr public keys. What is that? That's a public-private key pair where the private part is the alpha, which is sampled from the group G. The pub key is generated to the power of alpha, and the pub key can be known to anyone. The private key alpha can be known only inside the shard. Okay, so let's see how the user what they need to do in order to make the assets appear on some chain. So they need to sample some random Greek letter row. So they need to sample some row from the group G, and they need to have good random. If the row is bad, it can be concluded where the assets will end up. So they will call deposit on the ZK connector with this triplet, the amount of FTs they want to lock, generator G to the power of row, and pub key to the power of row. With these two numbers, we're hiding to where we are sending, but there'll be enough information to prove on chain for which it was intended for. Let's see how. Okay, probably everybody here knows what a Merkle tree is. Just a bit quickly, with the Merkle tree, you can efficiently prove membership in log n. You only need the root hash, and you're able to tell whether some leaf is a part of the tree. So if you want to prove that hash H2 is part of the tree, you need to provide the Merkle path, which is H3, this one H01, H47. You just concatenate these two hashes, hash it with the same hashing function, and bubble up. If it's the same as the root hash, then it means H2 is part of the Merkle tree. So when we call deposit with this triplet, we actually insert this triplet into a Merkle tree that's inside the zero-knowledge connector. Okay, and each of the chain, they have an off-chain component, which is the ZK bridge, that will try to see if it was intended for them. They're observing the ZK connector Merkle tree, and they are trying to figure out if each new added leaf is intended for them. So how can they conclude if it was decided for them? So the G to row and pub key to row, let's call them P and Q. And by definition, the pub key is G to alpha. If we can prove, if you have this alpha, then P to alpha should be equal to Q. I mean, this is just simple maths. From 3 to 4, it follows. So each of these off-chain components, they have their own private key alpha. And if it was intended for Calimero chain C, then if this equation holds, then they can mint the amount that was locked here, and they know it was intended for them. And nobody from the outside can conclude to which pub key it was intended for. So we are hiding the pub key with this approach. Okay, so let's see how to do a withdraw, which is a bit more complex. So first of all, if user wants to withdraw some amount from Calimero B, they will first need to do the standard burn. Like, if it was just a simple FT connector, they would burn and prove that this happened through the relayer that would push the newest block Merkle root hash and etc. as I showed in the first part. So here I added, this is the simplified image. I added here the light client for each shard, A, B, C, and D, and we need to hide this information as well somehow, because the outside observer would be able to conclude from where the assets came from, just from the burn proof, which has some specific heights related to that chain. So each of these, whenever a relayer successfully updates the light client contract for some chain, there's another Merkle tree inside this ZK connector, where the latest block Merkle root hash will be added as a leaf into that second Merkle tree. Okay, so how do we withdraw? For this, we need to generate a ZK snark. And specifically, what do we want to hide? What do we want to prove? Okay, this got a bit broken here. I don't know why. So we want to prove that we know some private key alpha. So without showing anybody, we want to prove that we know some alpha, such that when we select leaves from the FT Merkle tree, such that the equation P2 alpha is equal Q for each leaf, and the values that we select need to be at least the amount we want to withdraw. And of course, all of these leaves need to exist inside the Merkle tree. Also, we need to prove that this Merkle root R is inside the all chains Merkle tree, which is the second Merkle tree. If all of this is correct, then we generate the ZK snark, which is also generated in the off-chain component, since this is the slowest part in the ZK bridge. And any NEAR account can then provide this ZK proof to the method withdraw on the ZK connector. Inside this method withdraw, we are verifying the ZK proof. If it's correct, user receives the NEAR, and we have hidden from where the tokens came from. And this is basically it. I have one more slide. They told me that I should put this, scan this QR code. I mean, Tekuno is powered by Calimero, so if you can scan this, you can win some prizes, and that's it.